Okay, so now we're going to be talking about equations. So in the first video, we talked about like terms. In the second video, we talked about the distributive property. Those are kind of the two tools needed to now be able to start freely solving equations. So we could have, talked about solving equations earlier, but again, I think it was a nice build up to get to the point that we're at now. So what is an equation? An equation is a statement that indicates that two quantities are equal to one another. So if we look at, for example, x is equal to 7, that is an equation. What this is saying is that x and 7, they're the same thing. They're looking in the mirror to one another. They're the same exact thing. So that is what we call an equation. So there is an equality amongst terms. A solution to an equation, that's the answer. So a solution to an equation is the value of the variable that makes that equation a true statement. So when I think about solving equations, because solving equations, I feel like this is one of the harder chapters that we'll be talking about. It's just a puzzle at the end of the day. An equation is just a puzzle that we use operations and the distributive property and combining like terms to solve that puzzle. Well, the answer to that puzzle is what we call the solution. And what we're really trying to find, what the whole name of the game is finding out what is this letter equal to. Whoever that letter is equal to, that is the solution. And that is the number, or that is the value, I should say, that makes these statements true. Every other case would make it false. So that's what we're looking for here. Okay. So if you notice, there's two things that we have to distinguish. So an equation and an expression. I really want us to make sure to pinpoint the difference between an equation and an expression because they are two different things mathematically, but they're easy to overlook to be the same thing. An equation, again, is a statement indicating that two things are equal. So we're emphasizing that the left and the right side are equal to one another. An equation is only an equation with this equal sign. That's what makes it an equation. Notice an expression, there is no equal sign. So way back when in chapter 1 or chapter 2, I cannot remember, when we were talking about expressions, the most we can do is simplify an expression, just combine some like terms because there's no equation. Equation is what allows us to actually go ahead and find out, well, who is x? And so on and so forth. So please be careful the difference between the two. One has an equal sign, one does not have an equal sign. An equation, you'll see the instructions will say solve. We can figure out who is that variable. And with an expression, the most we can do is simplify. Just combine any like terms if need be. And then just for some extra terminology, we have a linear equation in one variable. Oh, a linear equation in one variable is an equation that can be written of the form ax plus b equals c. So what this is really saying behind all these words is the reason why we call it a linear equation is you'll notice that these equations will just be in terms of one variable. So if you were to continue in higher level mathematics, there are equations with multiple variables. And also notice we get the word linear because the exponent of this is just 1. So if you were to continue in mathematics, there's, equations with x squared, x cubed, there's equations with x's and y's. Those are all outside of the jurisdiction of linear equations, and that's all outside our jurisdiction. So we're only going to be talking about linear equations. So with one variable, and that exponent is also just a 1. Okay, well, how do I solve equations? What do I have to do here? And again, they can be pretty overwhelming, but it's a step-by-step process. So you'll notice I did give quite a bit of homework because, again, I do believe that this is kind of the harder chapter. People struggle with solving equations just because it can be a bit overwhelming depending on how many steps you have, and also just not really being sure to know what to do. Practice makes perfect. So how do we do this thing? Again, this is a game. The whole name of the game is finding out who is this variable. What is this variable secretly what the variable secretly is. So kind of who's behind the curtain of this variable. The way we do that is with inverse operations to perform on both the sides of the equation until the variable is left by itself. So notice here, x equals 7. This is what we want our final answer to look like. Some letter is equal to some value. And that should be the true value. So only that letter, or I'm sorry, only that value is what this x can be equal to. So that's what I'm saying here. X can only be equal to 7 to make it a true statement. And again, the whole technique behind this is with inverse operations. So we'll kind of talk about that a bit more. But one thing I want to emphasize is this both sides of the equation. Whatever you do to one side, you have to do to the other side. So I don't know if you guys remember, I don't know how to draw this. I can't draw for anything. Like those scales, you know, like those like judicial scales. I don't know what they're called. Old-fashioned scales. You know what I mean? Scales. Well, remember, if you add something to one side of the scale, you tip the scale. If they both have, if they both have the same amount, the scale is equal to one another. So that's what an equation is you want to think of. Think of it like that scale. If you put something on one side of the scale and you want to balance it back out, you have to put the same amount on the other side of the scale. So that's what I mean by performing on both sides of the equation. The whole point of an equation, is you have to remind yourself, is equality. The sides of the scale have to be the same. So whatever you do to one side, you have to do to the other, because if you just do it to one side, you're tipping the scale then. So you have to be cautious with that. And you'll see with some examples as we proceed. So our first example, x minus 6 is equal to 18. Well, what do I want to do here? Again, notice here we have an equation. X minus 6 is equal to 18. That's what I'm claiming. But I don't know who this x is that makes this true, that makes the left and the right side equal to one another. Well, I have to find out how. I have to find out who. Well, how? By inverse operations. So at the end of the day, remember, we want until the variable is left by itself. So I want this x all by itself. But notice I have this minus 6 in the way from it being all by itself. So that is what we want to focus in on. So if I have x minus 6 is equal to 18, I want this minus 6 to go on the other side, because again, I want x to be completely by itself. Well, how do I do that? That is where inverse operations come in. So we want to then think, this is a subtraction symbol. It's x minus 6. Well, what is the inverse of subtraction? Well, the inverse of subtraction is addition. So I want to add 6 to both sides. Because if you notice, if I have minus 6 plus 6, that's just equal to a big fat 0. I have nothing on that side anymore but the x, and that's what I want. But again, this is tipping the scale right now. If I have just plus 6, so I have to add 6 to both sides to balance back what I did. So if I have x minus 6 plus 6, that's left with just x, because I would then have 0. And then I have 18 plus 6. Well, 18 plus 6 is 24. So that's what I'm claiming is my solution. I'm saying that in order for this to be true, x minus 6 to be equal to 18, this x, it has to be a 24. The beauty of solving equations is we can check them. So how do we check them? Well, we take our solution and we just plug it back in. If the left and the right side are not equal to one another, we know we made a mistake somewhere. So let's go back and plug it in. This x, remember, we're claiming is really just equal to a 24. So I have 24. Well, I had x minus 6. So 24 minus 6 is equal to 18. That's what I'm claiming to be true. Well, 24 minus 6 is 18. So that means we have the correct solution, because 18 can only be equal to 18. If you have 18 apples and I have 18 apples, we have the same amount of apples. But if you have 17 and I have 18, that's not the same amount anymore. I don't necessarily care when it comes to the check step. Like, and you don't, or not me personally, but you don't necessarily care what these numbers are. It could be 1,000 is equal to 1,000. It does not matter what those numbers are, because this is the solution here. This is the answer. This is the check of the answer. So all you care about is that you have on the left and the right side the same number, because again, that's what makes it a true statement, because the left is equal to the right. If we got 17 is equal to 18, we know somewhere here we made a mistake. So I will heavily emphasize the check step because I think it's super nice because it helps avoid making mistakes. Okay, let's do some more. Oh, I already did. Oh, Jesus. Forgot to erase this. If we have 7 plus 11 is equal to 14, again, that 7, z plus 11 is equal to 14, that z needs to be left alone. Well, the 11 is currently in my way. Well, if I have plus 11, what do I have to do? I have to do the inverse operation, so I have to take 11 away. But remember, whatever you do to one side, you have to do to the other side. You don't want to tip the scale. So then I'll have z plus 11 minus 11, that's a 0. So this would be really just z plus 0, which is just equal to z. That's why we want to cancel it out. And then I have on the right-hand side 14 minus 11. Well, what is 14 minus 11? 14 minus 11 is 3. So that's what we're claiming to be the solution. Well, let's go ahead and check it. Well, again, I'm claiming that this z really just is a 3. So wherever there's a z, I'm going to plug in a 3 because I'm claiming that they're the same thing. So I'll have 3 plus 11, and that should be equal to 14. Well, if you notice, 3 plus 11 is equal to 14. So we know that this is the true solution. And it's only 3. 3 is the only number, because think about it. If you plugged in 4 plus 11, that's not 14. If you plugged in 2 plus 11, that's not equal to 14. It's only 3. That is the only answer that can make this puzzle true. Okay, let's keep going. So we have 15 plus 6y is equal, or I'm sorry, 15 plus 6y minus 5y is equal to 4 minus 9. This is where you want to first combine some like terms. So notice I have a 6y minus 5y. That's a like term that we can go ahead and combine. And then I have 4 minus 9. So sometimes on the individual sides, on the left and the right side, you want to check out, you want to simplify them first, because then as you continue with the equation, you just have less moving pieces. So we have 15. Well, what is 6y minus 5y? How many y's do I have here? Well, that's really just 1 y. Because 6 minus 5 is 1. So 15 plus y is equal to, well, what is 4 minus 9? That will give us negative 5 because I have more negatives than positives. Well, now if you look here, again, y needs to be left alone. That 15 is in my way. Well, if I have plus 15, I have to do the inverse to it. So I have to subtract 15 to both sides. 15 minus 15 is 0, so my y is left alone. And then I have negative 5. Let me move this down a little bit. And then I have negative 5 minus 15, which gives us negative 20. So we're claiming that negative 20 is the solution. That is the answer to make this left side equal to the right side. Well, if we look at the check step, again, I'm always going to be an advocate for the check step. These y's are really just negative 20s. That's what we're claiming here. So we have to plug them in and see what happens. See if the left and the right side become true. Remember, if the left and the right side are not equal to one another, like not the same number. So notice when we plug in negative 20, I get 15 plus 6y, but again, y is really just a negative 20, minus 5, yet again another y, which is really just negative 20, is equal to 4 minus 9. Well, I want to simplify all of this left-hand side to get 50 minus 120 plus 100. And then if I simplify the right side, I get 4 minus 9, which is negative 5. Well, once I simplify this whole left side, I get negative 5. So notice I got the same number is equal to the same number. So that implies here your work is correct, and that y equals to negative 20, that is the answer. But again, if you did all this work and you got negative 4 is equal to negative 5, or I don't know, like negative 9 is equal to 5, whatever, any other numbers that are not equal to one another, you know somewhere here a mistake was made. So you have to go back because your solution is not correct. This is the check step to verify that this is a true statement. And this is a true statement. -5 is equal to -5. That's where a little bit of logic comes in. So we have to be cautious. Again, I highly recommend doing the check step because it really saves you if you made any mistakes, and it kind of just gives you that calm peace of mind. So since the check step was good, y equals -20, that is our solution. That's our answer. Okay, let's look at another one for this video. Okay, what do we notice here? So -1 is equal to 3 times x plus 4 minus 2x. What's the word I got to use? I have to distribute. I can't do anything until I distribute. So let me rewrite this. I got to distribute. Well, I'm going to distribute this 3 since that's what's blocking me from solving this equation. I have to distribute this 3 to everyone inside the parentheses. Then I can continue combining like terms, if any, and then I can continue solving for x. So I'll have -1. What is 3 times x? 3x. Plus, follow the same operation, 3 times 4. What is 3 times 4? Well, that is 12. Minus 2x. And again, notice on the right-hand side, I have some combining of like terms that I can do. I have a 3x and I have a minus 2x. Instead of just looking at a bunch of x's, we can combine them down to just have one term because again, we're solving for that. So I'll have -1 is equal to, well, now if I combine like terms, 3x minus 2x, how many x's do I have? Well, 3 minus 2 is 1. So I have just 1x. And then I'll have x plus 12. And again, it doesn't matter what side the variable is on or anything like that. It's just whatever side the variable's on, everything else has to go to the other side. So it doesn't necessarily matter. A lot of times we're just used to the left-hand side belonging to the variable, but again, it does not matter. Well, remember, I want this x alone. This 12, though, is in my way. Well, if it's plus 12, what do I got to do? Minus 12, right? Okay. Well, now if on the left-hand side, I have -1 minus 12, that's -13. And then I have x plus 12 minus 12, this goes to 0. So it would really just be x plus 0, but again, which is just equal to x. So this is what we're saying is our solution. But again, let's go ahead and look at the check step. So remember, wherever there is an x, now a -13 will go since we're claiming that those are the same thing. So notice I have -1 3 times x plus 4, so this will turn into -13 plus 4, minus 2 times x, so minus 2 times -13. And once you simplify this with order of operations, you can then see that we end up getting that -1 is equal to -1, which is a true statement. That is absolutely true. -1 can only be equal to -1. It's like looking in the mirror. That's what we care about, that we got the same number on the left and the right side, because that implies that this is true. Again, if we got some other number like -2 is equal to 4, well, that's not true anymore. So here we can see that our answer is -13. And then we're going to continue with some more equations in the next video.